Well, let's see what we can do about that. So, all right. So that last lecture is like really, high level. What is all this computing stuff? What is embedded computing? So now let's do embedded control. So this is sort of specifically what we as, especially mechanical engineers, what we want with computing. There's a lot that we'll do with computing in terms of analysis, right? Like we're going to write MATLAB scripts or Python code to do different analytical work, but that's a completely different world from the embedded computing world. And what that is we're trying to put some sort of usually feedback control into a product, into some maybe manufacturing process, let's say. And you can't write MATLAB code. Well, it's hard. You can hardly say anything anymore. Like there's like so many subtleties. It would be rare for one to write MATLAB code to control some process that's going on a shop floor. There are some exceptions, but most of the time we're not going to do that. We're not, especially if we're going to build, like for instance, like the speed controller for a conveyor belt or something like that, and we're going to be like maybe mass producing these and selling them to lots of manufacturing customers. We would never write that in MATLAB. We would never write that in Python, probably not. We would write that in C, and we would write that for an embedded computer, not for a personal computer. So it all revolves around control, though. That's really what we're doing with it, is we're doing control. So let's talk about that for a minute. Feedback control is a powerful idea. A desired system state is compared to a measurement of its actual state, and some actuation is applied such that the difference between the desired and the actual state, which we call the error, is minimized. So, for instance, say we have a height controlled platform, and it is at this height here. We want it to be at this height here. We measure this height. We know which height we want it to be. The distance between those is the error. And we're going to do something to the platform, like for instance, actuate it with a power screw or something like that, to make it go from this location to that location, to make the error smaller. 0 preferably. So that's sort of like the idea of feedback control. We measure the error, we do something to the system to try to change the fact that there is error associated with it. This concept has been realized in many ways since around 300 BC, when the Greeks used a float valve to regulate the flow of water to a relatively constant rate, allowing them to measure time. So if you can regulate the flow of water to a constant rate, then you could say like, oh, when you fill up this bucket, like you better be back by 5 buckets worth of fill up. Then it would be, a specific increment of relatively constant time. And so the Greeks from about 300 BC, that's the first evidence that we have of people using this concept, although it's probable, because we don't have evidence of everything that's happened, so probable that there was something that happened before then that was like this. It's hard to say. Now, this is a human-used feedback control. Biological processes use a ton of feedback control in them. Our bodies are filled with feedback control systems. A lot of like measurement and changing of response based on a certain state. Regulation of like body temperature is an example of that. regulation of oxygen levels, of all kinds of things have these feedback mechanisms. For instance, if you try to hold your breath for a long time, all kinds of different system responses will happen to try to get you to breathe, right? If you're asleep, and you're like me and you have sleep apnea, you go to sleep and you stop breathing, your body will wake you up to start you to breathe again. And it might even need to use adrenaline to do that, which really sucks when you're sleeping. But yeah. Human created feedback control, we have evidence back to about 300 BC, which is a while. The 20th century, especially its latter half, saw a mathematization and vast improvement of control. Electronic circuits began to perform the key logic function. For example, if A is measured, then do B. Previously, the mechanical organization of the system had to perform the logic, as in the flow regulation example illustrated in figure 1.2. So let's go down to the figure for a moment and take a look. So on the left, we've got this system, and then on the right, so on the left, we've got the mechanical version. On the right, we have the embedded computer version. You can do this task with the version on the left. If you want to control the level of the water in this tank to be constant, then if this starts to fill up, so say the water level rose to here, that means that your float valve, so a float is going to be something that stays at the height of the water, right? So it's going to rise, it's going to go up, and the valve closes, or at least gets more closed than it was, and so your input stops or slows, and you're still flowing out. So that means it's going to make the level drop. If the level drops below that, the level that you want it to be regulated to, then you have the situation where this goes down and this happens, it opens the valve, and water flows in, more water flows in, faster and faster and faster. The further down this goes, the faster the water is going to flow out until it gets back to the sort of calibrated height, the desired height. So, does anybody know of a system that uses this? Toilet uses this. I mean, at least American toilets do. I don't really know. World toilets are like a whole thing. There's like different kinds of toilets everywhere. But in the U.S., toilets, the tank fills up with a float valve. It's a pretty good system, although mine gets stuck a lot. You got to jiggle the handle. Probably should open it up and fix it once and for all, but instead I just, wait to hear if the thing falls or not and jiggle the handle. So we aren't like really very good at making good decisions. We say, I could save 5 minutes right now if I just jiggle the handle instead of actually fix this. And so you do that for several months, and you waste 5 hours of time. So it's great. And then, so this is the mechanical version, and it's really good. And so for a toilet, that's a great system. Works really well. They do break, but it doesn't break very frequently. It's pretty reliable, cheap, does the regulation. Now, you could replace that with a microcomputer, and you probably wouldn't want to do it on a toilet, although I have seen a lot of like electronic toilet stuff out there, so maybe you would. But most of the time, you're probably not going to want to do that for a toilet, but for a more complicated system, you might want to, especially if you wanted more control than this afforded. Like this pretty much gets you stuck at a certain level. Like once this thing is calibrated, you can't change what the level is going to be, right? On this system, you could easily determine which level you wanted it to be at and change that on the fly whenever you wanted to.
Also the breakdown time, if this one, in some year it might break, but for that one it might last longer also.
Yeah, and it really depends on the hardware. So sometimes the mechanical system is more reliable, sometimes it's less reliable. Just kind of depends on what you use. If you use plastic parts over here, those things tend to break pretty quickly, but if it's a nice old tanker toilet, it might last for a long time. So this is the microcomputer one. Essentially, what the difference here is that you measure the water. Once again, you're going to use a float. The sensor is going to have to somehow change that displacement into an electrical signal, right? So you can buy lots of sensors that would do that. There's tons of different types. So your instrumentation and measurements class should go through a little bit of that discussion, but lots of different options there. And then on the valve actuator side, I mean, there's going to be a valve again, so nothing different there, but that valve's going to be actuated by some electronic means somehow. So often a solenoid or something like that would be in control of the valve. And what the microcomputer does is it takes in a voltage that correspond from the sensor that corresponds to the level of the water, and it takes in and then it puts out a valve actuator signal, so say like a solenoid signal or a motor or something like that actuates the valve, and it makes the decision about what to do. So notice that it's performing this sort of decision and logic function. So in this case over here, this linkage took us from a movement of the float to a movement of the valve. And the way, the choice in the lengths of the arms, this one being this long versus this one being that long, the shape of that linkage, those where it's pinned, those have influence on how this decision is being made, or this logic is being made. And it's cool, and it's adjustable to a point, right? And you could maybe contrive to have an adjustable version of this. That's the part that the microprocessor completely just substitutes in for. So that's the only part that we're really changing. Everything else is kind of the same. Nothing else really changes other than the fact that the logic, the decisions are being made by the microprocessor instead of the physical systems orientation. So sometimes in a control problem, we're going to talk about three different aspects. There's the process. So that's this tank that has water at different heights. There's the control hardware. So that's the sensors and the actuators. Sensors and actuators are typically called control hardware. And then there's the decision and logic, which happen inside the microcomputer. So this is the same as over here, but the decision and logic, instead of being made at by the linkage, it's being made by the microcomputer. All right. As circuits have evolved into increasingly powerful microprocessors connected to sensors and actuators, the complexity of implementable logic has grown drastically. But one constraint is persistent. Decisions about how the control system should respond with its actuators, given the system's current state, must happen in real time. That is now. It has to happen right now. So you measure the current state of the system, and you want to change that in some way by actuating something. Like, for instance, you measure the height of the water. You need to actuate your valve in accordance with what you want. Like, for instance, maybe the water's too high. You want it to go lower. You have to put that output, that valve actuator out as quickly as possible. Okay? So you can't just like take in an input, measure a whole bunch of levels of the water, and then like at some point later decide to do some actuation. As soon as you know what the level is, you need to do some actuation. So you have to be doing that. It has to be responsive to the situation. So they call that real-time computing. And of course, we know that now is never quite possible. We're always lagging a little bit behind, but as close as possible if we want. Real-time computing for control must not only be fast, but controllably so. That is, the programmer must be able to direct timing. This is one of the more difficult aspects of real-time computing, is that you not only need to know, you not only need to be able to go fast, but you need to be able to know how fast you're going. So you need to know how much lag there's going to be between this measurement and this output. You need to know how many real seconds in the real world are going by while you do a certain calculation. So timing in real-time computing is a really big consideration when you're doing embedded computing for control purposes, embedded control. But it doesn't really matter when you're like, it doesn't matter as much, I guess, when you're working on a desktop application. We'll wait a second for the wheel to spin, like it's fine, loading. Yeah, so, I mean, we don't like it, but, everything is as fast as possible. And actually, we always want it to be as fast as possible, but we don't really have any concept of what the real time in the world, like when people write software, they might measure like, oh, what is the lag, just to like see how long it's taking to do a certain operation, doing like benchmarks and stuff. But they're not that worried about the difference between, say, like 50 microseconds and 60 microseconds. That might not even be, like, for them, that's roughly the same. Whereas in an embedded computing situation, being able, 10 microseconds might be a significant amount of time to deal with. It might not be something that you need to have control over all of that. So, yeah. So although computing power has improved steadily, real-time computing remains among the greatest challenges for control systems engineers. Most feedback control is instantiated with embedded computers because sensors and actuators must be nearby to increase reliability and decrease lag. So if the feedback control was to happen, like, so there's no reason in principle that you couldn't, say, have, let's take the example of a car. Cars have tons of embedded computers in them nowadays. And in principle, you could just have all the sensors on the car, dump all their data into one place, stream that to Google's servers, do the calculation on the server, stream it back to the car, and then make your decision about what to do on like the intake or whatever. But the communication part of that is usually the weak link in terms of speed and in terms of reliability. So most of the time, our embedded computers are there because we want to cut out that link. And actually, that was originally a lot of computing was done. So people would have a terminal, and there would be a mainframe computer that was in another location. That's what they was actually doing the computing, and you had an interaction with it. So the cloud is that too. So the cloud used to be the only way to do computing, and now the cloud is like a new thing, but it's an old thing that where we send off our instructions to be computed elsewhere, and then we get the results. And that concept works well for some things, but when it's time sensitive, it doesn't really work at all. When you need to know what you need to do right now, when you're doing a feedback control situation, you can't have like your internet drop out for a second, or you can't have it really lag on some packets come back. That would really kill, it's obviously really wouldn't work in a car, but even in other applications, doesn't work. It's not very effective. Plus, having that communication infrastructure often is difficult. So, like if you're in a car, if you're out in the middle of nowhere, no cell service, there are ways to communicate, like satellite stuff, but reliability, not great. So and expensive, that type of thing. So your communication aspect, you tend to want to cut out. So you do an embedded controller, an embedded computer for doing the calculations, for deciding the logic for what to do next in that situation. So therefore, designing controllers, that is embedded computers and peripherals used for control, that's what a controller is, requires an understanding of embedded computing hardware and its programming. I want to stress that we can get kind of like really enamored with the computing aspect of this, and it is really important to understand. That's a lot of what we're doing in this class, but we are just trying to learn it at the level that we need in order to be able to write embedded control software and interact with a device. So we're getting this. So you guys have heard of the term stack, right? Like your stack is like your skills, like your stack. You add to your stack this layer of a being able to do embedded computing. As a mechanical engineer who understands how to model a dynamic system, how to control a dynamic system, and can actually help build the hardware system, that's just another real, nice thing to have on the stack. Whereas, we're going to leave the actual development of computing architectures to those folks. We have to understand it to an extent. Like, you get something from memory. We kind of understand what that is. We kind of understand how the CPU works. We kind of understand these things. Because when we write in C, we have to understand a little bit. But we probably aren't going to try to worry about, developing a new instruction set for like a new architecture that we're developing for a computer. I mean, not to say that we couldn't, but that's just not what our focus is in this class, at least. That's what really, as mechanical engineers, typically our focus is how do we interact with this at the level of being able to program in it, being able to make it do what we need, without necessarily being able to design those systems ourselves. We'll let the EE folks and the computer engineering folks and computer science folks worry about building those actual micro circuits and stuff. So we'll talk a little bit about how to do digital circuits, but we're not going to be too worried if we can't design like an awesome digital circuit. It's okay. So, yeah. Okay. Question.
What does it mean? Understanding embedded computing hardware in this case?
Yeah, so in the next lecture, we're going to be talking about a way to understand how computing hardware is usually set up, like the CPU and the memory, and how an instruction would come down and be executed, and the result that would come out. What happens inside a computer? So over the next about a week, I think we should have a pretty good understanding. So like this, end of this next lecture, and then a little bit next week, pretty good understanding of how it works, broadly speaking. Not necessarily every aspect of everything, but we're gonna deepen our understanding in certain ways as we proceed through the class. But understanding it at some level, not necessarily the very, very deepest level, but decent level. Does that make sense?
Yes.
Okay. Cool. I think it'll become more clear too.